This is a schematic of a nuclear reactor. The nuclear reactor consists of control rods, which can be lowered in and out of the reactor. We've got fuel rods, which are these parts here. We've got a moderator, which is coloured black. And on the outside of the reactor, we've got a coolant, and that coolant takes heat from the reactor to a heat exchanger, so that the heat is taken away to be used elsewhere. Finally, the whole thing is encased in a steel and concrete casing, which is around about 5 meters thick. Inside a nuclear reactor, there are control rods. Control rods move out and into the nuclear reactor. Their job is to soak up excess neutrons to stop the nuclear power station going supercritical. Coloured red are the fuel rods. It is here that the nuclear reactions take place. The fission processes where atoms are split, which generates lots and lots of heat energy. The moderator, coloured black, has the job of slowing down fast-moving neutrons. If neutrons are travelling too fast, they won't be absorbed by the nucleus of the fuel, and therefore won't cause a fission process. So we need to slow them down with a moderator. Just outside the nuclear reactor, which is coloured white, is a coolant. The coolant takes heat away from the nuclear reactor. The coolant then transfers its heat to a heat exchanger. This allows heat to be taken away from the nuclear reactor to be used to turn water into steam and drive turbines. Around the outside edge, coloured grey here, is a 5 metre thick steel and concrete container. Its job is to stop radiation escaping from the nuclear reactor, which will cause damage to any workers. Let's take a look at how a moderator works. Natural uranium, which is used as the fuel in any kind of nuclear power station, mainly contains uranium-238 with a small proportion, around about 1%, of uranium-235. Both undergo fission processes, that is to say that the atom splits when neutrons are absorbed. So the neutrons fly around in here, and when they get absorbed, a fission process takes place, generating lots of heat. The problem is that sometimes these neutrons are flying around too fast for uranium-235 to absorb them. So what we have to do is slow them down. So we use a moderator made of something like graphite or heavy water, and as these repeatedly hit the moderator causes them to slow down with each collision. That way they then are allowed to move slowly and be absorbed by the uranium-235. Uranium-238 can undergo fission processes using the fast neutrons. So these fast neutrons are absorbed by the atom, causing fission processes. That way, all the atoms that make up natural uranium can be involved in the fission process. Nuclear fission is where a neutron is absorbed by a large nucleus such as uranium-235 or 238. When that happens, it becomes unstable and splits into two smaller nuclei. When this happens, it generates lots and lots of heat, but also creates on average, three neutrons. Those neutrons can then go on to create further nuclear fissions, and those can go on to create even more nuclear fissions. If we're getting more nuclear fissions than we started with, we've got a situation where we're supercritical. This means the reaction is out of control and could cause a large explosion. This is similar to what happens in a nuclear bomb. If we can create a situation whereby one neutron produces one fission process, and from that one useful neutron creates another fission process, then we've got what's called a self-sustaining nuclear reactions. When this happens, what we can say is we've got a critical mass. If we get too many neutrons created, we get out of control. If we get too few neutrons created, then the reaction is not self-sustaining. Supposing we've got a small amount of uranium fuel. During fission processes, neutrons are created. Those neutrons have got two choices. They either go on to create further nuclear reactions, or they can escape from the sides. Ideally, we want a situation whereby each fission process creates one suitable neutron, which will then go on to create another nuclear reaction. When this happens, we say we've got a critical situation. If we go on to create too many neutrons, then what happens is the reaction goes supercritical. If we've got too many neutrons escaping through the sides, then we've got a situation which is called subcritical. Let's take a look at a larger mass. When a neutron is created from a fission process, the larger the mass, the more chance it's got of staying within the fuel, therefore creating further nuclear reactions. If this mass is too big, then we could have a situation which would send it supercritical. If the mass is too small, then we've got a subcritical situation. The ideal situation is that for every one neutron created, two neutrons escape from the sides. This is approximately a piece of nuclear fuel of around about 10 kilograms in a spherical form. Safety considerations of a nuclear reactor. Large quantities of potentially harmful neutrons, gamma rays and beta particles are produced within the nuclear reactor vessel. There are also things called antineutrinos which are produced, but because they do not interact with matter, they don't have any effect on anybody working around the nuclear reactor. The beta particles have very limited range and are easily stopped by the walls of the reactor vessel. Neutrons and gamma rays, however, produce very little ionization and therefore are extremely penetrating. As a consequence, extremely thick walls are placed around the nuclear reactor. These walls are around about 5 meters thick and are made of concrete. This protects the personnel who work in the vicinity of a reactor. The coolant within the reactor is at a very high pressure. Therefore, we have to contain it within a pressurized vessel. Sometimes this pressurized vessel is the actual 5 meter thick concrete walls. Fission. The fission process can be stopped simply by inserting control rods to the maximum extent. They are made in such a way that in a situation which is supercritical, these control rods drop under gravity into the reactor. That makes it safe because if there's a power cut, then they would just drop automatically and shut down the nuclear reactor. The fission products continue to produce energy through radioactive decay, which just happens naturally, and this cannot be stopped. If the cooling system were to fail, the heat produced by this process would melt the core. This is a meltdown situation. The reactor is designed to contain the core even in this eventuality.